Hi, and welcome to module number 49. Recall that the overall theme that we're discussing is sparse recovery, and we saw that L2 is analogous to having a sphere around the origin blown up with a balloon with more and more air until it hits a hyperplane, until it's tangent to a hyperplane. That's not good. That's no reason to believe that that solution would be sparse. L0 is excellent for preserving sparsity, but computationally infeasible. So we moved to L1, and that took us to lasso, and that took us to cosamp, and that took us to asking what's the best that we can do. And it's a very complicated question. It's a very complicated design space with a lot of knobs that you might be interested in. And we're starting to understand that there are bounds on how well you can do if you think about it as a communication system. And in this module, we're going to look at a precise single letter characterization of optimal signal recovery. So first of all, several words here. Precise. Instead of a bound, a precise characterization. What type of characterization? A single letter characterization. Single letter means that there's one expression, one symbol, one quality, that one equation that you work through, and you don't need to solve a vector optimization procedure with a lot of variables. You just need to solve a scalar optimization problem, a scalar equation. So that's one aspect. Precise, not a bound, a single letter characterization, no need to consider the optimal code of some very high dimension and so on. And finally, optimal recovery. Not low complexity recovery, not computational complexity in NP, meaning polynomial recovery, optimal recovery, the best that you could do. And what we're going to see, this is joint work that I did with Gangning Guo, who you see in the upper picture, and Shlomo Shammai in the lower picture. What you're going to see is that this precise understanding of optimal recovery actually leads us to an understanding how to approach realistic low computation approaches. And that'll be the next one. So what type of characterization are we looking for? We have an input vector x of length capital N, and suppose that we're only going to look at one entry, xn. Now, this vector of length capital N goes through, we can think of it in information theory terms or communication system terms as a channel. There's going to be a density for the noisy measurements y conditioned on that vector x and the measurement matrix phi. And after this channel, we'll have, again, the noisy measurements y. They're going to be in Rm, m for measurements. And we'd like to estimate xn. And we'd like to do so, we'll call our estimate xn prime. There's no reason to believe, at least under some simplifying assumptions, let's say that the input is IID, the matrix is IID, the channel is IID. There's no reason to believe that there's no difference between x1, x2, and x capital N. So we'll just take one of the xn's. We're going to estimate xn prime. Now, you're estimating xn prime from the noisy measurements vector, and also you have access to the matrix phi. And we want to estimate x. Now, if we knew the posterior distribution for x, conditioned on everything that's known, y and phi, that would be great. So ultimately, we want to have an understanding, what can we say about xn, that one location, given the noisy measurements y, which is a vector, and the matrix phi. And if we know the posterior for xn conditioned on y and phi, this is a sufficient statistic. With a posterior, you can calculate anything that you want. You can calculate the mode of the distribution. You can calculate the xn that minimizes the L1 error, the xn that minimizes the L2 error. You can view it as a communication problem and say, hey, I want to know, I want to do classification. Was it -1 or +1? So is a sufficient statistic. You can do statistically anything that you want. However, it's a complicated distribution. It's n-dimensional. It's computationally intractable. It's because it's n-dimensional, it's also mathematically, it's hard to understand. And what we like ultimately is a simple characterization of its quality. And we'll approach this simple characterization by considering the large system limit, where the number of elements in the vector x, the input vector n, goes to infinity, and m, the number of measurements, the ratio between m and n, as n goes to infinity, is fixed, okay? The limit is equal to delta, and delta is positive. So we're looking at y is equal to phi x plus noise, and there's also that square root of gamma here, and x is getting larger and larger, and as x is getting larger and larger, phi is also getting larger and larger, n is getting larger and larger, and y is getting larger and larger. And importantly, the aspect ratio of the matrix is constant. Maybe there are 3 times more columns than rows, or maybe 4 times more, whatever it is, that aspect ratio is positive. And we call this situation where m and n are growing the large system limit. As before, unit column norm, as before, square root of gamma has a interpretation of signal to noise ratio. So we want to estimate xn, y equals square root of gamma phi x plus z, and we're only focusing on xn. And let's begin with a hypothetical setup. Suppose that the rest of x is available. How is it available? Somebody told you that. You guessed it, it's side information, not important. Well, if it's available, then maybe we can subtract it off. So we have here y equals square root of gamma phi x plus z, but we're only interested in xn. We're only interested in this purple location. But xn is multiplied by column number n. So what really happens here is that we started with, let me write this in a text box. We started with y equals square root of gamma times phi times x plus z. And now I'm saying we can subtract off the rest. So this part and this part multiplied by this part and this part is going to be available to us. So let's call the other part of the matrix as phi not n, and let's call the other part, the rest of x, x not n. N is the index that we're interested in, and we know the rest, and we can subtract it off. So now I'm saying we know x not n. We obviously know phi, all of phi. So now let's think about it. Phi times x is equal to phi n multiplied by xn plus phi not n multiplied by x not n. If that's the case, then y is equal to square root of gamma multiplied by, in square brackets, the expression from the previous line, plus z. Okay, we're getting somewhere. So now let's think about where we are. Well, y minus phi not n, or rather we need to subtract square root of gamma times phi naught n times x naught n. Again, recall, x naught n is given to us. Doesn't matter how, it's given to us, so we can subtract it off. We call this y tilde. So define that. Well, y tilde is going to be copying that expression, but the phi n, or rather phi naught n, x naught n part is removed. So what we have is that y tilde is equal to square root of gamma times phi n xn plus c. That's it. Now, of course, you can modify the notation, but and later there are supplements about all the things I'm discussing, detailed supplements. But the bottom line is that now you have phi n is a matrix, xn is a scalar, c is a column vector, y tilde is a column vector. How can we estimate xn from y tilde? So we know phi, because of that, we know phi n, the remaining column that appears here, and we also know y tilde. We've subtracted off the rest of x. So what do we do next? So I'm saying, want to estimate xn from y tilde and phi n. All right. So those of you who have some communication courses in your background will know that what's happening here, Z is additive white Gaussian noise. Okay, that was in our model. And the proper way to address this type of problem, these were vector observations equals vector phi times scalar plus vector noise. And we want to estimate the scalar xn. The optimal communication way to do this we use a matched filter. A matched filter means that we multiply everything by phi n transpose. All right, so now let's think what's happening here. Phi n transpose times y tilde is equal to square root of gamma times phi n transpose times phi n times xn plus z. But now, I'd like to remind you that phi has unit norm columns. If they have unit norm columns, well, what is phi n transpose times phi n? Phi n transpose times phi n is an inner product between a row version of that column and itself. An inner product between the row version of the column and itself is the squared L2 energy there, which in this case is equal to 1. So phi n transpose times phi n is equal to 1. And then we have that phi n transpose times y tilde is equal to square root of gamma times x of n plus, I forgot earlier, phi n transpose times z. All right, so now let's think where we are. I'm going to sketch this. So we have that phi n transpose multiplied by y tilde, the guy from above, is equal to square root of gamma times 1 times xn. Xn is a scalar, plus phi n transpose, again a row vector, multiplied by a z, column vector. Now, this row vector, phi n transpose times y tilde, gives us a scalar. You know, maybe we can call it, I don't know, y tilde n or whatever notation you'd like, is equal to square root of gamma xn, again, xn is a scalar, plus phi n transpose z, let's just call it, I don't know, z tilde n. You can have whatever notation that you'd like. Now, what is the distribution of z tilde n? Recall that z is a Gaussian random vector. Each of its elements are independent of one another. They're independent and identically distributed, IID, and each of them has zero mean unit variance. Now, there are results that if you multiply a Gaussian random vector, if you multiply it by any matrix, what comes out is, again, a Gaussian random vector. In this case, it's going to be a Gaussian random scalar or a Gaussian random variable, RV for random variable. And it has a mean and it has a variance. So it's distributed, well, zero mean at the input multiplied by any matrix, in this case a row vector, is zero mean, and the variance can be calculated. Now, without going into details, I'm just going to tell you, phi n transpose is a row vector that has unit norm because it's a transpose of the column vector with unit norm. Z, each of its elements had variance 1, and it can be shown that the variance of this guy is 1. So we have a new variable. Let's say we call it yn tilde, whatever notation you like. It's equal to square root of xn, or square root of gamma, multiplied by xn, plus standard zero mean unit variance Gaussian noise. Okay? This is the hypothetical case when we know the rest of x. So y tilde is square root of gamma xn plus z tilde. Z tilde, again, is a standard Gaussian random variable. And therefore, you can think about it as a Gaussian random variable centered around expected value, square root of gamma xn, with variance 1. Or you can think that you have xn, you multiply it by square root of gamma, you add standard Gaussian noise, let's call this n, and you're getting y tilde. What I just jotted down in a block diagram sort of sketch is equivalent to what we actually end up having here, except for one change. Instead of square root of gamma, we're multiplying in the realistic scenario. The hypothetical was that we can subtract off the rest of x. In the realistic scenario, we don't know the rest of x. It's unavailable. We estimate xn from a noisier scalar measurement, where the eta is a degradation term. And recall, we want a high SNR. We want gamma to be large. And now eta times gamma is smaller. It's degraded. Eta is less than 1. Now, why does all of this happen? Again, there's going to be much more details. You can look at the supplements. But I'm going to give you a brief explanation. So what happens is that we subtract off an estimated version of x not n. All right, what is that estimated? So x hat not n is equal to the true x not n plus, suppose that element by element, you're going to have some mean squared error. Now, you'll note that I'm assuming that every single element in x not n, there are capital N minus one of those, every single element has the same mean squared error. Why does this make sense? I'm assuming that x is IID. The matrix is IID. Well, it can't truly be IID because it has unit norm columns, but as far as we're concerned, it's fine to assume that statistically on average they have norm 1. That's good enough in a large system limit where the size of the problem grows. So everything here is symmetric. There's no difference between x1, x2, and x13. There's no difference between error in estimating element number 1, element 2, and element number 13. So we'll just call it the mean squared error. So now what happens is that when subtracting off, we add a term of the following form, phi n transpose. Recall that the phi n transpose multiplied by the phi n times xn, well, we had, in the previous slide, we had phi naught n transpose multiplied by phi naught n multiplied by x naught n. So now we have square root of gamma, which is multiplying all of that, that's S and R, square root of gamma times phi naught n transpose times error naught n, or rather phi naught n times error naught n. So before subtracting off, we had square root of gamma phi naught n error naught n, maybe with a negative sign, maybe with a plus sign, depending how you define error naught n. And we are multiplying by phi naught n transpose, and so we have square root of gamma phi naught n transpose phi naught n error naught n. Now, recall that we're in the large system limit. Because we're in the large system limit, phi naught n transpose times phi naught n has some statistical properties, okay? So it's going to be two large matrices multiplied by one another, multiplied by error naught n. And error naught n, each of the elements there has expected value 0. If it didn't have expected value 0, you might as well subtract off the expected value. Also, like, it's a poor estimator, right? 0 mean and some variance MSE, the mean squared error. And we're multiplying that by this large matrix. And what happens is that when you have all of these elements mixed together, and they all have, presumably, the same distribution, the central limit theorem kicks in. And that means that what we're subtracting off resembles Gaussian. As we look at larger and larger problems, it's closer in distribution to Gaussian. And that means that we have extra Gaussian noise. And that's why we have a noisier scalar channel. So let's let's revisit. Here, I was saying in this sketch that in the hypothetical case, I didn't have an eta. X was multiplied by square root of gamma plus standard Gaussian noise. That's what I was performing scalar estimation from. So this process is a scalar channel from xn to here in the block diagram, it's called z. You could, earlier, I think we called it yn tilde. It's a scalar channel. And from the scalar channel, we can easily calculate the posterior because this scalar channel it has a simple structure, right? All we're doing is multiplying by square root of gamma and adding standard Gaussian noise. Well, when we have more Gaussian noise, we have a noisier scalar channel. And then we do have an eta with reduced signal to noise ratio. So again, a lot of details, a lot of information to supplement, but here's the main result. We have a single letter characterization that where conditioned on when we're looking at xn, the observations are statistically equivalent to a Gaussian random vector, or rather, I'm sorry, a Gaussian random variable centered around square root of gamma times eta. So the degradation is the eta multiplied by xn with unit variance Gaussian noise. Now, just to make this clear, this is equivalent to, in quotation marks, in quality, n, xn, and the amount of noise would be 1 divided by, rather, the amplitude I take square root of eta times gamma times xn. I multiply by, or rather I divide by square root of eta times gamma. And that would mean that the Gaussian noise, it no longer has unit variance. It was multiplied, or rather it was divided by square root of eta times gamma. So its amplitude is proportional to, in whatever units, square root of eta times gamma. Now, if that's the amplitude, the variance, rather, let me say the standard deviation, used to be 1, and now it's 1 over square root of eta times gamma. Now, the variance is quadratic in the standard deviation, and because of that, the variance of this Gaussian noise is 1 over eta times gamma. So now I'm saying that we have a system centered around expected value xn, and the variance is 1 over eta times gamma. So if gamma is large, let's say 20, and maybe eta is half, and therefore eta times gamma is 10, now the variance is going to be 1/10. 1/10 meaning not too big. And that makes sense because we said that the SNR is quite good, and despite the degradation, the eta, it's still maybe not quite as good, but rather good. The variance is 1/10. Now, so let's see where we are now. So we understand that this is the distribution. It is statistically equivalent to in the large system limit. And additionally, eta, the degradation, can be calculated with a fixed point equation. This fixed point equation is going to be provided on the next page. We explain in a very heuristic way how we get to the fixed point equation in the supplements. And as I explained on the previous page, what we're really doing, we're subtracting off, in the hypothetical case, we were subtracting off a perfect estimate of x not n, or rather its impact on the noisy measurements y. And what we're doing in the real problem is that we're subtracting off a noisy estimated version of x not n. So the estimation quality is just as good as a noisier scalar observation. So this is no longer, we had a very complicated high dimensional posterior, but we've now understood, we have an insight that deep inside the posterior, in the large system limit, there will be something that we call decoupling. Each xn, when we estimate it, the posterior will be decoupled, statistically decoupled from the other locations in x that are being estimated. So here are the details. Eta is going to be strictly between 0 and 1. Again, the SNR went down. It's a fixed point of this equation. Again, this equation appears in the supplements. And the take-home point is that we have a degraded scalar channel. Now, this entire explanation, clearly what I did, but also in the supplements, is not non-rigorous, owing to the replica method with a symmetry assumption. In words, the replica method with a symmetry assumption is where I said, hey, we can use the central limit theorem. That is not rigorous. There are some cases where the replica method has been shown to be imprecise by a few percent. In many cases, the rigorous, the methods where the replica method is used for analysis, in many cases have been shown to be rigorous, to be precise. So the same type of analysis was used in CDMA detection as early as 2002 by Tanaka, later by my co-author Dongning Guo and Verdu in 2005. More recently, there have been rigorous derivations of this fixed point equation and the decoupling, for example, by Reeves and Pfister in 2016, and by Florent Kerzakala and co-authors also in 2016. I'd also like to point out a related analysis by Rangan, Fletcher, and Goyal from 2009. They showed the quality of the MMSE estimate, but not the posterior, meaning that they didn't show the decoupling aspect using, again, the same work of Guo and Verdu. So that'll be all for this module. I know that there's a lot to comprehend. I suggest that you go and look at the supplements. But the main point here is that we now have a decoupled posterior for a noisier scalar channel. In the next module, we're going to use that to put together reasonable complexity algorithms that achieve these limits, or rather get very close to these limits, again, in the large system limit.